Hey guys, this is Srini and welcome to another video on the topic of semantic segmentation. In the last video, we looked at various backbones for Unet architecture, meaning we looked at how VGG or ResNet or Inception, how these backbones can be used as part of encoder for a Unet network. And in this video, let's actually look at different architectures. So let's pick ResNet as our backbone, but then how does Unet compare against LinkNet? Again, these are two different architectures. Again, both are designed for semantic segmentation. Both are fully convolutional networks. And the goal is do you need to worry a lot about picking one or the other? First of all, how do you use this? And the next thing is, how do they compare against each other, right? So before jumping into the code, a quick background about this, so you at least are a bit informed. I always urge you to read the original papers. Again, Unet, as we mentioned in a couple of videos already, it's from 2015, the golden year when it comes to publishing a lot of these architectures. And it's a convolutional neural network primarily designed for biomedical image segmentation. But as you'll realize, it works on most types of semantic image segmentation. Now, LinkNet is again a bit recent, well, 3 years ago or so, 3 to 4 years ago. And this is designed for semantic segmentation, as you can see from the title here. Again, these are if you just do a quick Google search, you'll find these papers. And I really encourage you to read this to understand exactly what LinkNet is and exactly what Unet is. Okay, but at a high level, what does it mean? I mean, we talked about this in the last video, right? What does it mean to use VGG or ResNet or Inception as backbones? Well, for Unet or LinkNet, you have an encoder and you have a decoder side. Okay, the encoder part is where we can use a backbone, like for example, a pre-trained VGG. Okay, and leverage from this transfer learning. We already have the weights, for example, from our ImageNet. Okay, training of VGG. In this example, today we are going to use ResNet, but either way, you have the weights. Okay, so this is basically what we mean by the backbone. But what we are talking about, I mean, this we talked in the last video. Okay, what we are going to talk about today is using the same backbone, for example, ResNet, but then on two different types of architectures. Okay, Unet, again, I talked about Unet in many videos. LinkNet, this is the first time I'm talking about it. And here's a quote out of the original paper by these authors. They say, they propose this deep neural network. Why did they do this? I think the primary goal here is allows it to learn without any significant increase in the number of parameters. So they basically don't want to scale things up, because as you go deeper and deeper, as you make the networks complex, of course, the number of parameters increase, right? So they claim that, or they say that they have 11.5 million parameters, and this is supposed to be efficient, and it potentially performs better in segmenting live stream videos, if this is what, especially if you want to deploy this on embedded systems. So I'm going to let's jump into the code. I have another slide with all the summary of exactly what my findings are. We'll get there in a minute. Okay, but let's jump into the code. Okay, let's not waste any more time. Okay, so, well, I promised to jump into the code, but I'm just flashing a screen up here that shows the GitHub repo for segmentation models, because it's not an easy thing to write, these backbones and, the code for all of these. And it's also not a good use of your time to kind of reinvent what is already out there. So I'm going to use segmentation models as the library that feeds us the models, and, whether it is Unet or LinkNet, and also the backbones. Okay, exactly the same we have used in the last tutorial. Just to refresh your mind, in case you haven't watched the previous tutorial, we can actually use any of these architectures. FBN is very slow. I do not know much about PSPNet, and I haven't tested this, but Unet and LinkNet, let's compare these two for this tutorial. Okay, of course you can test all of the other ones if you want. These are all the backbones, and let's actually pick ResNet as the backbone. and compare these two. Okay, so just a quick note here. Now let's go ahead and get into the code. I'll leave all the original links as part of the links to the original papers as part of the description. and you can go ahead and look at those. And again, there is a paper here. I gave a link where they kind of compared between various backbones. They don't have LinkNet, but they have something called AD LinkNet, which is not what we are going to use right now. So I'm not showing that, but again, good resource. It makes a great read. Now, again, instead of wasting your time looking at the screen while we are loading data and training it, I have already done that. As you can see, I mean, you see the last output that is the prediction for LinkNet is almost 2 minutes, right? So we'll get there. So let me go through this line by line. I'll explain this, but we'll not be executing this as we go along. So these are all the libraries that we are using. Again, nothing new here. The only thing that's new is probably this import segmentation models as SM. And again, go ahead and follow these guys when it comes to installing segmentation models. If you haven't done that, this is very straightforward and easy. Okay, you just do pip install segmentation models. It should be fine. Okay, so just follow the instructions here. But once you are done, you should be able to go ahead, import this in pretty easily. Everything else is very straightforward. What else? I think that's nothing else to explain here. And now I'm going to resize everything to 128 by, in fact, my input dimensions are 128 by 128. So let me jump into what we are going to use. I took a bunch of large images and corresponding masks. And again, if you want to label your own images, I recommend you to go to www.APEER.com, APEER.com. It's free. You sign up and you upload your images. You can paint it. That's the slow part, right? I mean, you can paint all the pixels and then save them as your masks. So I did exactly that. Where I ended up with my large images. I chopped them into 128 by 128. So I have these 128 by 128 size images and corresponding masks. You don't see anything here. Oftentimes I get questions that, hey, I did my segmentation, but my images look dark. Well, they look dark because you are probably, after segmentation, your labels are probably 0, 1, 2, 3. But when you open this in Windows, right here, it doesn't. It tries to display everything from 0 to 120. 0 to 255. So it looks dark. So use a program like ImageJ or download like ZenLite, ZEN or ZEN. LITE, ZenLite from Zeiss. It lets you work with many types of images. So if I just go ahead and adjust my brightness contrast, I know my lowest value is 0, my highest value is 0, my highest value is 3 or 4. Let's go ahead and do 4. As you can see, there you go. So now you see the image. It's not like they're dark. I mean, again, this may sound too basic to most of you, but again, if you're not familiar with this hopefully can be very useful. As you can see, each pixel has a specific value, and the values go from 1, 2, 3, 4. Okay, we'll re-encode this to 0, 1, 2, 3 because that's what most libraries like. If you have these type of segmentation. So anyway, now going back to the data, I have 1600 such masks and images. Okay, so this is where we are starting. So and number of classes equal to 4. As we just saw, right? 1, 2, 3, 4. So I'm reading my training images and my training masks. Okay. Again, not much to explain. Play with the code here. I'm using glob to walk through each image, load it, and append it to my list and convert the list to a NumPy array. So at the end of this, I'll have a NumPy array of train images. If I go back up here, yes, train images, you see 1600 images, 128 by 128 by 3, right? I'm reading them as color. Because my network I'm going to define is expecting an input image of 3 channels, right? So that's exactly why I'm reading this as RGB instead of gray. And masks, I'm reading it as gray because masks, again, you just have one channel with 4 different values. Okay, so that's exactly what I'm doing for masks. Okay, nothing tricky. As I mentioned before, I'm encoding the labels. So my train masks encoded original shape. If you look at my encoded original shape, all the values, instead of going from 1, 2, 3, 4, now they're going from 0, 1, 2, 3. Now I'm doing this. I add this step just in case. Maybe your masks are not 1, 2, 3, 4. Your mask may be one region, with a pixel value of 20, the other one with a pixel value of 55, the other one 78. We don't know. Let's encode them to 0, 1, 2, 3. So it makes it easy for us to handle later on. Okay, that's the whole point of this encoding the labels. Again, run each of these lines independently to make sure it makes sense to you. Again, if you are a beginner coder. Now, np.unique train masks encoded. If I run this line, you should actually see that, okay, my unique values are 0, 1, 2, 3, right? So these are all the pixel values in my images. This is just a sanity check to make sure everything is working fine. And then I expand the dimensions, as we always do, because now if you look at train masks input, it should be 1600 images, each 128 by 128 by 1 right there, okay? And this is train masks. If you look at train images input, where is that? Train images will get there. Sorry, train images is basically we are assigning it to x1 and x2. Again, let's go to the next line. So I have my train images, right? Train images again 1600 by 128 by 128 by 3. So I have 1600 images. So again, we have the train images coming from up here. So 1600 images. Now, with what are we doing with these 1600 images? Now again, one quick question: why am I expanding the dimensions for masks and not for the images? Well, you have to do this for images if you read them as grayscale. Because I'm reading them as RGB, I already have that channel ready, right? That number ready as 128 by 128 by 3. Again, basics, but you never know who's watching this video, and these type of information can drive you crazy if you're new. Okay, I hope you appreciate the extent I go through to to cover the little topics. Okay, let's move on now. So now we have our train images and train masks. We just need to divide that into training and testing data sets. So that's exactly what I'm doing here. In fact, I'm holding out 10% of our data for testing. Now, why do I have another line to further split this? Well, initially I was testing. I don't have a lot of resources. I don't want this system to work with all 1600 of my images or even like 1200 of these images because it's very slow. Even though I have a GPU with 4 GB, it's a bit slow. So I just wanted smaller size. So I'm just taking only 50% of the remaining, which means now I'll be working only with 720, sorry, how many images? Just a second, x_train. Let's look at xtrain and see how many images we're working with. xtrain, 720 images, yeah. So we're gonna work with 720 images for training and 160 images for testing. That's it, okay? I'm just using this to split it, that's it, no tricks. Okay. Now, the next step is converting it to categorical. This is very important. I talked about this in a couple of videos ago when we talked about multi-class semantic segmentation, right? So when you're doing multi-class semantic segmentation and when your network uses categorical cross entropy as or most of the loss functions for multi-class, they expect the input to be the shape of categorical. Okay, now if I actually go down here, let me quickly where am I fitting? Why train categorical? You see, this is exactly what I'm talking about. When you do give your x and y as part of your model.fit for validation or training, you're giving your testing data and categorical data, right? So that's exactly why we are converting our data into categorical. Again, please watch my tutorial on categorical, which is just a quick summary. The regular masks, the values are 0, 1, 2, 3. Okay, at a given pixel, the value can be 1, for example, and the next pixel, the value can be 2. But when you convert to categorical, at each pixel, you have 4 values. Okay, and only one of them has a value of 1, and that one corresponds to whatever the original pixel label is. For example, if the pixel label is 1, then the second value will be 1 and everything else 0, because you have 0, 1, 2, 3, right? 0, 1. And if the pixel value is 3, then the last one is going to be 1, everything else 0. This is why it's called one-hot encoding. Okay, a quick summary on our categorical, but again, convert your masks or labels into categorical. This is very important. for your multi-class training, right? Okay, now this part, again, we covered this a couple of times. How many classes? Number of classes, 4. And what activation are we going to use? Softmax, right? Because it's going to give us the probability for each of these classes of the categorical classes. In categorical, we have 0, 1, 2, 3. At the end of all the training, when you do the prediction, it's going to give you probability for what is that pixel's probability being a 0, being a 1, being a 2, or being a 3, right? And then we say, oh, every value, sorry, every class will have some probability. It's never 0 to 1. It's always some probability. So we'll say, okay, the maximum of these probabilities is the class I'm going to assign this to. If my class number 2 has a probability of 0.6, everything else below 0.6, obviously, then, okay, for this pixel, I'm going to assign a class number 2. Okay, again, basics, but you never know what's important. Okay, so activation is softmax. Our learning rate is going to be 0.301, and I'm going to use Adam optimizer at a learning rate of 0.0001. Okay. I'm going to, these are the lines that I copied from these segmentation models where they gave an example. And this can be very useful when you actually do semantic segmentation, right? I mean, instead of using accuracy as your metric, because accuracy doesn't mean anything when it comes to semantic segmentation, because one majority class can be, you're doing a great job, but the minority class, you're not doing as good of a job, right? Then accuracy will probably give you 95%, but in reality, the minority class is so crap, okay? So that it's unusable. So that's why we use dice loss or focal loss. Okay, again, look at focal loss. Again, focal loss is great when it comes to balancing unbalanced data sets. Also, handling data sets where one phase is easy or one region is easier to segment compared to the other. And dice loss is another loss right there. So in this case, we are calculating dice loss and focal loss, and we are actually summing them up, right? I mean, you can do 2 times focal loss if you want to put more weight on focal loss, especially if you think you have unbalanced data sets. But our final loss that we're going to use is dice plus focal loss, okay? And our metrics that we're going to use is intersection over union square and the F score, from the segmentation models.metrics. So this is the loss function. These are the metrics, not accuracy or not categorical cross entropy that we are using, okay? Typically, you'll use categorical cross entropy for your loss function, and accuracy, let's say, for your metrics, okay? And we are tracking 2 metrics here, so we are going to provide that as a list. Moving down, again, this is something we covered in the last tutorial. Our backbone one, well, there is only one backbone we are going to use in this exercise, ResNet 34. And we are going to pre-process the data using however it was pre-processed using backbone. This is, again, very important because you have to get the data into the same type as you have for ResNet 34, right? This is why I haven't normalized my data. I'm just using my regular 8-bit pixel values. So, okay, now moving on. I'm going to, now I define what preprocess is. Now I'm applying preprocess to my training and testing data sets. So now I'm ready with my X and Y. Okay, so let's go ahead and build the model. How do we build the model? Okay, my model number 1 is segmentation models.unet. Okay, so these guys have Unet and LinkNet, and using the backbone 1. And what weights to use? ImageNet, right? I mean, if you import these ImageNet weights, then it starts with those weights and then you continue the training from that point. How many classes? 4 classes. We already defined that. And our activation function is sigmoid, which we just defined, softmax, which we defined up there, okay? For binary classification, that would be sigmoid, okay? This is multiclass, so I'm using softmax. Okay, so that line makes sense, and then we are going to compile the model, and to compile the model, you have to give the optimizer, the loss function, and metrics. The optimizer is, where did we define? Our Adam, right? That we defined up here. Our loss is the total loss, which we defined here, and metrics are these 2 metrics that we need to track. That's exactly what we are doing. As you can see, I did experiment with Adam optimizer, categorical cross entropy, and these metrics that we defined here. Again, you can experiment on your own time. And then I just started my timer to see how long does it take to actually train this model, and trained it for 50 epochs, and looked at the execution time. So for this one, it took 38 minutes 47 seconds, right? Almost 39 minutes. And then I saved the model, I saved the history if you want to look at the history. I did exactly the same for LinkNet. It's very easy. All you need to do is change Unet to LinkNet and you're all done. That's it. Okay, that's exactly what I did. I also checked the time, and let's actually look at the execution time. And the execution time here is 33 minutes 26 seconds. So about 6 minutes faster with LinkNet on this data set. Now, if you are training this for like 2 to 3 days on a lot of data, right, then this difference will be significant. So even in like 40 minutes, you can see how we kind of saved 6 minutes right here by using LinkNet. So definitely on my system, LinkNet is slightly faster, a few percent faster, but it's not like, okay, LinkNet took 5 minutes versus 40 minutes, right? It's not a humongous difference, I would say, on my data set, on my limited data set. Again, like I said, this can add up if you have faster GPUs and tremendous amount of data that you train for a couple of days. Okay, so that's there, and one lesson there. So LinkNet is a bit faster. Okay, then comes how do they train? So first, let's look at history. I haven't optimized this to kind of do both plots at the same time, like for Unet and LinkNet. But first, let's plot our loss for Unet. So here is how the training went. Okay, it did converge up to 20, and after 20, I see some overfitting right there, right? I mean, not that bad. I mean, the validation is still very, pretty good. The loss is staying down, and the accuracy for validation is a bit lower than for the training data set. This is expected. This looks very nice. Now, how does it actually compare to our model number 2, which I saved as history 2? And if I plot this, let us have a quick look. And there you go. This looks very similar to the other one, actually. If you look here, up to about 20, up to about 10, it's actually getting better at a faster rate. If you look here, same thing, up to about 10, it's getting better at a faster rate. But after 20, again, there is a bit more fluctuations here. There's a bit more fluctuations up and down. But overall, I think these both, the performance-wise, they both are very, very similar. Very similar. In fact, if I run this one more time, I'm pretty sure this will be slightly smoother. Again, yeah, I'll leave it to you to check that, but as you can see, I don't see a clear advantage for either of these when it comes to training. Now, what do we do? Let us go ahead and let's skip this IOU. Again, you can go ahead and print out the intersection over union values with both, but let's actually do it in a different way. Let's segment a whole bunch of images and then look at how close these two segmentation results are. Okay, visual is much better, but let's actually do the visual part right now on single patches, right? I mean, we held out a bunch of data for testing, so let's randomly pick an image from our testing, data, and then segment it using both Unet and LinkNet. Okay. This is Unet. Sorry, this should be Unet. Okay, LINK. LinkNet. Okay, so now LinkNet. I don't know why I made that mistake. Model underscore. Let's be sure now. Model underscore LinkNet. This is what happens when you copy and paste code and then forget to fix it. Okay, so we are predicting here using model.unet, and then we are doing argmax, right? Again, when you predict it, it gives you an array of four values, and then we are picking the max and assigning our class to that. That's what argmax actually does. And we are doing argmax exactly, LinkNet. Okay, let us do this and plot the output to see how good the input and output are. Obviously, I was looking at Unet segmented images and I was like, whoa, both images look exactly the same. But I was making a huge mistake there, but let's find out if that's really, let me move this up so you can see it. So here is the original image. And this one on the right hand side is the testing label, the original label, and bottom left is the Unet result, and top right is the LinkNet result. And as you can see, now these two are slightly different. You see this little piece right there? I hope you guys can see these 2 pixels, the red pixels. Here we have 1, 2, 3, 4 or 5 pixels. The original one has 3 pixels. But look how close the results are compared to the original label. Amazing, both with Unet and LinkNet. Let's run this a couple of times to see. And here is another area where all the results look almost identical, actually, to our original label. Let's run this one more time. Look at this, and again you have this small red blob right there, which corresponds to this bright region, and you have these blue areas, and you have these other lighter blue regions. I think this is very good result, actually, compared to your original image. Now that's okay. Now the next thing what I've done is I have a folder full of images that are 768 by 768. Now I'm talking about a large image, the entire volume. Now I wanted to segment this entire volume, all the images, and compare how much faster LinkNet is at segmenting these compared to Unet. Now instead of doing all 462, because it was taking a little longer, I wanted to record the video. I took a subset of those and dumped them into a folder called 50 large images. Okay, instead of 468, I just did 50 images. Still gives us good, decent idea about how long it took for each of these. So the bottom part here, again, I talked about Patchify in a couple of videos in the past, which is a great library if you would like to divide your large images into smaller chunks and then do something to those images and then put them back, right? So I'm using that basically to extract 128 by 128 by 3 patches, apply our prediction, like in this case LinkNet.predict on these single patches, and then put the patches back as, where is it, unpatchify, right? Put them back into my large image, and then save it into an array, and finally dump the array into a TIFF stack, like a 3D volume, using our TIFF file. Again, I'll let you experiment with this, but here we have a prediction time. Let's go ahead and I didn't store, I think Unet is stored here. So how long did it take to time_Unet? We'll get to summary in a second, but let's actually look at this. And LinkNet prediction time is 1 minute 59 seconds, like 2 minutes. And the other one, we'll have a look at that in a second. I'm not sure why it's printing out in this format, but that's okay. One final thing. I saved all of this into, let me just show you, this is the moment of truth, into segmented images, and this is the volume that represents the Unet. This is the volume that represents the segmentation from LinkNet. Okay, so I opened them in again, any of your image processing programs. Like if you look at this versus this, right? So let's open this and look at the adjust the brightness contrast, auto. I hate auto because it goes from 1 for some reason, because our minimum value is 0. There you go. And then let's go to this volume, adjust brightness contrast, set 0 to 3. Okay, so here it is. So these two volumes, they look identical in terms of how they the output looks like. There are some changes, I mean small minor differences between these two. So if I randomly go to a different image, again, this is the entire volume that you're looking at the screen. Now visually this may not be that easy to interpret, so what I did is I took one image and subtracted the other from this image just to see how many of this are misclassified. So that's this image. Isn't this amazing? Very few pixels are kind of different from one image to the other. Okay, almost the entire volume, we segmented them in a very similar way. So what am I trying to convey here? the core essence is the quality of segmentation for my dataset that I segmented is identical whether you use Unet or LinkNet. Okay, now let me just flash the final summary screen so you at least get an idea of what we are trying to learn here, at least what we learned using our dataset here. Okay. So here is the final summary. When it comes to the training, I think both have very similar structures. You see the Unet is on the top, LinkNet is down here. Very similar behavior, both when you look at the loss and also the IOU right here. Both are approaching about 90% IOU right there. Not much of a difference. And trained on 720 images, 128 by 128 by 3. And then we predicted on 50 images, each 768 by 768. When you break them down into patches of 128 by 128, that means we have about 1800 images each of this. Now, final summary, Unet training execution time 39 minutes and LinkNet 33 minutes. Unet prediction time 2 minutes 12 seconds and LinkNet 2 minutes, right? 1 minute 59 seconds or so. So about 12 seconds difference for 1800 images. So for all practical purposes, I think both are very similar. I mean, a better test would be on like a video, streaming video, to see how each of these actually performs on these videos, which hopefully one of you guys can do, or if I find time to do those, I'll add to that my to-do list. I have a pretty long list to get to. So I hope you learned something from this video. Again, every video is supposed to be educational. I am going to give you the code, all the code that you see here, so you don't have to write your own, although I recommend putting your own code, for these type of applications. But again, you can always build on top of what I am sharing here. If you have something cool, please share it as part of the comments so others can benefit. Again, please do not forget to hit the subscribe button and like this video, because I am pretty sure you absolutely love this video. Thank you.